In this chapter, we're going to talk about the atomic structure, which is the discovery of the atom, the particles, and the periodic. First, the atomic theory. The first atomic theory came around from a Greek philosopher by the name of Democritus during the 5th century. And he proposed that everything was made up of indivisible particles. And his theory kind of got buried a long way until about the 19th century when John Dalton, an English scientist, studied this further and came up with his own theory. But it was very similar to what Democritus had proposed. Democritus did not really have a lot of information, so whatever he proposed was pretty good for his times. These were the elements known in the 5th century. Okay, really very, very few elements. So I thought you might. So here is Dalton's atomic theory. He says all matter is composed of indivisible atoms. An atom is an extremely small particle and it retains its identity during the chemical reactions, which means nothing happens to the atom. It stays as it is. An element is a type of matter composed of only one kind of an atom. So which means that if the atom is different, then you have a different element. So for example, an element of gold is going to have a different kinds of atom than element of iron. Now, this theory was kind of challenged a little bit later on as we learned more about the atoms. And now we know that all atomic structure is pretty much the same. There's a very few things that are different about them. However, this is still true that each atom will have only one kind of an atom, which also has been challenged, but we'll talk about that. Okay, so then a compound is composed of an atom which is made up of two or more elements and it's combined in a fixed proportion. And in a fixed proportion also means actually in whole numbers. So you will never find a compound that is made up of a 1.5 atom or half an atom or 1/3 of an atom. So usually the proportion is 1:2, 2:3. It's all whole numbers and it's fixed proportion, which means that when we're talking about a certain compound, they're all going to have the same kind of a proportion. All right, the last theory of Dalton is the chemical reactions. This is also a very important law actually. It's called the law of conservation of mass. And what this states is that in a chemical reaction, a rearrangement of atom takes place, okay? And so nothing is created, nothing is destroyed. You can start with a certain set of compounds and you may end up with a whole other set of product, but the number of atoms that you start with and the number of products that you get will be the same, okay? Or the number of atoms that you have in that product is going to be the same. So for example, in the combination of oxygen and carbon to form carbon dioxide, you will have a set number of carbon atoms, or this is oxygen atoms, and then carbon atoms, and these atoms will still be present in the final product. Okay, so nothing is lost, nothing is gained. This is also called the law of conservation of matter, and this is a very important law for any matter. By the way, you do have to know the Dalton's atomic theory. Whether you know them in this order or not, that's a different thing, but otherwise you do have to know them. Although if you look at it, this is kind of written out nicely, starting from an atom to element to compound and then to a chemical reaction. So there's a certain gradient to the theory. Now, the law of definite proportion. This law states that different samples of a given compound is going to have the same mass ratio. Okay, so for example, you can take any amount of carbon dioxide, okay, but the mass of oxygen to carbon is going to remain the same, okay, in it, no matter how much sample you start with, because the ratio of carbon and oxygen in carbon dioxide is fixed, okay. Same thing can happen if you start with carbon monoxide, which is CO, and in that case again, the mass of oxygen and carbon is fixed no matter how much of carbon monoxide you start with. So this is called the law of definite proportion. Then there is a law of multiple proportion, and this states that if two elements can combine in more than one form, then those are going to be in ratios of small numbers. Okay, so for example, the ratio of oxygen in carbon dioxide and the ratio of oxygen in carbon monoxide is 2:1. Okay, no matter how much of the two substances you take. That's the law of multiplication. Now for the atomic structure. This is again a very important part, very fundamental for chemistry. There are three particles that are found in an atom: electron, proton, and neutrons. Okay, neutrons and protons are found in the nucleus, which is the center of the atom, and electrons are found outside. These are the properties that we have for neutron, proton, and electron. So for example, neutron is found in the nucleus. It doesn't have any charge, and this is the mass. Look at the mass, 1.673 times 10 to the negative 4, 24 grams. That's very, very tiny. Proton, which is also found in the nucleus, has a positive charge and has exactly the same mass as the neutron, 1.673 times 10 to the negative 24 grams, very small. Electron, which is represented by E, is found outside the nucleus. This is the only particle found outside the nucleus. It has a negative charge and its mass is 1,000th smaller than the mass of the neutron and the proton, okay, which is 9.109 times 10 to the negative 28. All right, so about 1,000 times smaller than neutron or proton. As far as the atom is concerned, the mass of electron is considered to be weightless, okay, pretty much. The weight of neutron is considered to be as 1 AMU, atomic mass unit. The weight of proton is considered to be 1 AMU, atomic mass unit. Who wants to remember the gram weight? Nobody does. Okay, so we can't remember these numbers. So right now we're just going to refer to them as AMUs, and later on we'll learn about some specific units that we can give for atoms. In any case, these are the three particles which you have to know. You have to know the location, you have to know the charge. Regarding the atomic structure, how the atomic structure was discovered, it's a huge study that was undertaken over 30 years by many scientists, because these particles are so small, as you can see from the mass, that it took a really long time and a lot of research to come up with all of these three different particles in it. So in the next few slides, it's just a little bit of a historical description, which I will talk a little bit about, but you can read a lot more in your textbook. So the first particle that was discovered was the electron, and this was discovered by J.J. Thompson in 1897. So you can see it's not a very old particle, at least till when it was discovered. It's been around, but we didn't know about it, okay, until so late. He used what is called the cathode ray tube and observed that a radiation that was coming out of the hydrogen gas was deflected by a magnetic plate. And he concluded that the particles that were coming out were negative, okay, from there. And they were always negative no matter what element he used. The first thing he used, the first element he used was the hydrogen gas. But he could start with neon, he can take argon, he can take any other gas, and he would still get a negative charged ray. Because they were negatively charged, their mass, their charge to mass ratio was calculated to be this number, which is a negative number, okay, which is, this is the charge per gram, okay, it's a very small number. These particles, he named them as electron, okay, and you should see the next slide, which has the experiment. Try to go on the YouTube link over here to actually see this in action. It's a really neat experiment, and you can see that this is the cathode. This is where he applied the gas, and once he charged this, this is the ray that was produced, which was deflected by the magnetic plate. That was positive and negative. Okay, so go through this on YouTube and see the Robert Milliken experiment. This one was to establish the charge on the electron. What J.J. Thompson found was the charge per gram of the electron, and what Robert Milliken found was the charge of the electron. And what this did is to help find the mass of the electron. Okay, so using this experiment and J.J. Thompson's experiment, they found out what the mass of an electron is, which is very light. And of course, you can't measure that much, so it has to be only calculated. You can read more about the experiment in your textbook. Finally came Rutherford's gold foil experiment, and this came after the discovery of the electron, because any atom is considered to be neutral, okay? And so if there's a negative particle in the atom, there has to be a positive. The location of this positive particle was not known. The positive particle was called the proton, but the location was not known. And so Rutherford actually established the location of the protons. Initially, he thought that all the protons were distributed all over the atom. So which means that there is a circular space and there is negatives and positives all over, but his experiment established that there is a central location for the protons, for the positives, so which I'll show in the next slide. The last particle to be discovered was the neutron, okay, and that is because there was some mass differences. So for example, hydrogen, which has a mass of 1, has only one particle, which is a proton, so that was fine. But helium has 2 particles, okay? It has 2 protons, but the mass was 4. So how is that possible? Which means that there is some other particle in there. And so the particle was discovered by James Chadwick almost about 30 years later. And this was the hardest to discover also because it is neutral. Okay, so it has no electrical charge. But anyhow, it was eventually discovered, and neutron was found to exist in the nucleus of the atom, which is the center. So here's the gold foil experiment. And what Rutherford did is he took a metal plate and he irradiated that with the alpha particles. And what he thought would happen is that all the radiation will just pass through because the positive and negatives were all distributed over all the atoms, okay, everywhere. So the positive particles should just go ahead and pass through. But that's not what actually happened, okay? What happened is that some of the radiation got deflected, okay, away from some mass in the middle. This would not have happened if he had the original theory correct. But because his original theory was not correct, he had to change his whole model for the structure of the atom. So the location of the proton then went from being outside and distributed all over the atom to being in the center location of the atom. And so the alpha particles, which are actually positively charged, were hitting the nucleus, getting deflected by the positive in the middle because protons are positive and alpha particles are positive. So they got deflected by that and they went in a different direction instead of going straight. And because of this, it was established that protons are found in the middle, okay, and not all over. So finally, we have the atomic structure, all right? And this is called the Rutherford atom, or the nuclear model of the atom. And in this case, here's the nucleus in the center with the protons and the neutrons, and outside are the electrons. So this is a nuclear model, or you can also look at it as a planetary model if you wish, because the sun is in the middle and everything else is around it. So that's how the structure of atom is. You have to know the structure, by the way, until we get to a future chapter where we will have to change some things, but until then, this is how it's going to be. So now for a few things about the atom itself. The atom has a few numbers that you need to remember. First one, the atomic number, which is the number of protons. Mass number is the number of protons and neutrons in an atom. The identity of an atom is by the number of protons, not by the neutrons, not by the electrons, only by the protons. The way we write the symbols for atoms is X for the atom. The mass number is A, which is written on the top, which is protons and neutrons, and the atomic number, which is Z, is the number of protons. That's written at the bottom. So here we have the two numbers and the symbol, okay, that's given to us. So in the periodic table, you will find that the atomic number is on the top instead of the mass number, because the periodic table is arranged according to the atomic number chronologically. So sometimes it's a little confusing that you see different numbers on the periodic table versus how it actually should be written chemically speaking. Okay, but it's a small thing and you kind of get used to it eventually. Okay, the other thing that I would like you to look at on the periodic table, if you have it handy, is that the mass, okay, which is the number of protons and neutrons, should be a whole number, because if you're just counting the particles, then the addition of two particles should be a whole number. If you have 2 protons, 2 neutrons, it should be 4. But it's not. Okay, there is a decimal point there, which means there is a fraction there. So which means if there is a fraction, there is something else going on. It turns out that elements have isotopes. And what isotopes are atoms that have the same atomic number but different mass number. The only thing that is different between two isotopes is the number of neutrons. If you change the number of protons, you change the number of positive charges. Electrons are not even part of the measurement here if you look at any of the atomic number or mass number, so we're not even talking about electrons. So the only particle that can change is neutron. Now if you remember, we were talking about Dalton's atomic theory, and in Dalton's atomic theory we mentioned that all the atoms in an element are alike. Well, they're still alike. So an iron atom is still an iron atom, but some of the iron atoms will have a different mass number, which means they'll have a different number of neutrons in them. So they're not all exactly alike. Almost all elements on the periodic table have isotopes. How many isotopes there are, you cannot predict that. Okay, and no one is asking you to do that. What is the proportion of these isotopes is also unpredictable, so you don't even have to do that. Okay, all you need to know is that each element has isotopes. Okay, and isotopes is different mass numbers, same atomic number, which means different number of neutrons. So how do we determine that we have isotopes? And this discovery actually came around very late because the mass spectrophotometer was not discovered until very late. Okay, it was actually invented, not discovered. So it was invented very late, and because of that, it took a little time before we figured out what isotopes were. Until then, it was considered that every atom is alike and every atom is the same with the same mass numbers, but it wasn't. So it turns out that once you put the sample through a mass spectrophotometer, which is what this is, it takes the sample, it converts it into gas, it passes through a magnet, and then there is a detecting screen. Okay, and so once the sample comes out, it is detected, and it detects it by mass to charge ratio. So you can find out what is the proportion of each isotope in any substance. Okay, and so that's what this is. And again, remember, in isotopes, the only thing that is different is neutrons, which means that chemically all of the isotopes will still behave the same way, but their physical properties will be slightly different. This is what the data looks as when it comes out. So you have the intensity of the peak, which tells you what the proportion is for, say, neon, which is the mass of 20, versus neon, which is 21 and 22. Okay, and so which means the number of neutrons are different. Okay, since the number of electrons are 10, number of protons are 10, the neutrons must be 10 over here, number of neutrons must be 11 here, and must be 12 here. So the proportion, if you can see, is 90.48% here, 0.27% for atomic weight of 21, and 22 is 9.25%. Could you have predicted this? Absolutely not. Are you required to? Nope. So don't worry about it. Okay, all you need to know is that isotopes are. So how do you calculate atomic masses? Well, you find out what the percent abundance is, okay, which is what was given in the previous chart. You know what the mass is of each of the isotopes that's coming out. And then what you do is you take the fraction of the abundance, which is 1.48 divided by 100, because it's a percent. So you take the fraction abundance, you multiply it by the mass, and you get the mass that is contributed by that particular isotope. Okay, you take the next one, the next one, next one. Okay, all of these are percents. You multiply it by the mass, and you get the mass that is contributed by that particular isotope. Once you have all the masses of all the isotopes, you add them together and you will get the average of all the isotopes in there. And this is how you do the calculation for calculating atomic mass. You can see that the mass is 207, which is way more than 203 because the contribution that is coming from this particular isotope is so less that it doesn't really contribute too much to it. Okay, so by looking at this number, you can really tell which is the most abundant isotope. Okay, because this is 207, so the most abundant isotope must have a weight of around 207. Okay, all right. Now for the periodic table. The periodic table is one of the most essential tool for chemists. You really have to understand the periodic table. If you don't understand the periodic table, then it's almost like you don't understand your ABCs, okay, in chemistry. So you really must understand the periodic table. So keep one handy with you all the time. So first of all, there are two things in the periodic table. There are elements that are arranged in specific groups and rows. It's a very systematic tool. And once you understand the periodic table, you really learn to appreciate how these chemicals and how these elements are arranged in there. And you appreciate the people actually who designed this. The first person to design this, not the first, exactly the first person, but one of the major contributors to the periodic table is Dmitry Mendeleev. He is a Russian scientist. You should see the small video over here. It'll take you to the history of the periodic table. And again, over here, there are some good resources, okay, for understanding what the periodic table is. Of course, if you go back a few centuries, you will find that the periodic table was actually very, very simple. There were only 4 elements: air, water, fire, and earth. But now we have more than 117 elements. What will surprise you to know is that the entire universe is made up of these elements. There have not been any new discovery of elements even in outer space. So we're still all made up of exactly the same matter. So here's the periodic table, okay? And first we're going to learn about some of the classifications of the periodic table. First, the periodic table is arranged chronologically by atomic number, not by mass. Remember, with mass you can have isotopes, so the masses can vary, but the atomic number is pretty consistent. So when you look through here, you can start from 1, which is hydrogen, 2, helium, 3, 4, and then so on and so forth. How this periodic table is arranged into these groups and into these rows, we will talk about that. Some in this chapter and a lot of it later on, okay, in chapter 7, 8, or 8, 9, okay, and so wait for it until then. First, the periodic table is divided into 3 different types of elements. All the ones on the left hand side, which are the greenish ones, these are called the metals. The yellowish ones in the middle, these are called the metalloids, and the blue ones, these are the non-metals. Okay, here are the properties of metals, non-metals, and metalloids. Metalloids are kind of in between. They're the borderline between metals and non-metals, which means they can behave either way. Okay, the properties of metals are that they are shiny, they're malleable, they're good conductors of heat and electricity, they're really hard, and they can give electrons to form cations. We will learn about this later in the chapter also. Non-metals, they vary in color, they're not really shiny, they don't conduct very well heat or electricity, they accept electrons, okay? And so this is the main difference between metals and non-metals. Group 7 and 8, these two over here, these two are completely non-metals, all right? Metalloids are in the middle. As I said, they can behave either way. The one exception to all of these elements is hydrogen. Hydrogen is a very unique element. Okay, it has only one particle, which is proton, and of course the electron, which is weightless. So it's still there though. So it has only 2 particles, I should say. Okay, a proton and an electron. It doesn't have a neutron. The placement of hydrogen in group number 1 over here is a little bit wrong because it's a non-metal, so it technically should be on the right hand side. You will see a number of periodic tables where hydrogen is also placed in group number 7, okay, and that is a wrong placement, but so is this. Okay, so in a lot of periodic tables, hydrogen is actually placed in the center. The poor thing is neither here nor there, okay, nowhere. And that comes from being so unique, okay, that you don't belong anywhere. But anyhow, that's what hydrogen is, okay? It's a very unique kind of a substance. Here are the group names that you must know as we go on, because we refer to our groups with particular names, okay? And so I've labeled here for you the first group, which is called the alkali metals. Now remember, hydrogen does not fall into that, okay? Hydrogen is not an alkali metal because it is technically a non-metal, all right? Group number 2 is called the alkaline earth metals. These ones in the middle, these are called the transition metals. No names for some of this, thank God, so you don't have to remember so much. Group number 7 is called the halogens. And then the last one, these are called the noble gases or noble elements. Okay, so you do have to remember all of these names. You should be able to classify the periodic table. If I give you an element from anywhere in the periodic table, you should be able to tell me where it belongs, okay, and what group does it. Elements and symbol. Um, all the chemicals are represented by symbols, by one or two alphabets. The first one is usually the capital, and the second alphabet is always going to be a small case. A lot of these element names come from planets, people, countries, etc. You don't have to remember all of that. However, as a chemistry student, you must remember elements 1 through 20 by heart, and all of the elements in group 1, 2, 7, and 8. Okay, and I will mention the rest in class, especially the ones in the transition metals. Okay. So before we finish off, let's go ahead and do some solved problems over here. And I'll walk you through some of these. So give the number of protons, electrons, and neutrons in one atom of chlorine 37. Chlorine 37 means that chlorine 37 is the isotope. Okay, chlorine can have many isotopes. So the one they want you to concentrate on is 37. When they say chlorine 37, that really means atomic mass, not atomic number. So remember, the atomic number of chlorine is not going to change because chlorine is defined. Its identity is by the number of protons. So the protons will always remain the same, which means if you have a chlorine atom, you can look at the periodic table and see that the number of protons or the atomic number for chlorine is 17. Okay, so once you know that chlorine is 17, you know the mass is 37. So the atomic number must be 17. The number of electrons must be 17 because the atom is neutral. So protons and electrons have to be the same. You subtract 17 from 37 and that comes out to be 20 neutrons. Okay, so C is the answer for this one. In the next question, which is an aluminum ion, aluminum 3 plus has, and if you look at all the options here for you, are protons and electrons. Now remember, electrons and protons are equal in any atom because any neutral atom has to have equal number of charges. Okay, so protons and electrons are equal. What 3 plus means over here is that you have excess of protons. So how many excess of protons? You have 3 excess protons over here because 3 electrons have been given away. So if you have aluminum, which has atomic number of 13, it must have 13 electrons also. But because it has 3 excess protons, it has only 10 electrons now. Okay, so you can look at it from two different ways. 3 plus meaning it has 3 excess protons. 3 plus also means that 3 electrons have been given away. Okay, and so D is the answer then, the 13 protons and 10 electrons. The atomic number is 13, so really B, C, and E will completely go away. Okay, you can eliminate those completely from there. 13 protons and 13 electrons means that it does not have a charge, okay, on it. The aluminum does not have a charge because these two particles are equal, okay, in number. All right, number 3, which of these elements are a good conductor of electricity? Neon, sulfur, helium, chlorine, or iron? For these ones, you will have to look at the periodic table. And in this case, you really need to know your symbols very well, so you know exactly where you're looking at. Neon is a nonmetal, sulfur is a nonmetal, helium is nonmetal, chlorine is also a nonmetal. So these are all found on the right-hand side of the periodic table. Iron is a transition metal. As soon as you have a metal, you have a good conductor of electricity. It's as simple as that. So you have to know iron and the symbol of iron, otherwise you will not be able to find it in the periodic table. Last question, who is credited with discovering the atomic nucleus? Dalton, no, that's the atomic theory. Gay-Lussac, who? We haven't done that yet. Okay, Thompson, no, Thompson was for electron. Milliken, no, he found out the mass. And so it's Rutherford, he is the one who figured out that atom actually has a nucleus, okay, to it. Here are your keywords and concepts for this chapter. You have to know the Dalton's atomic theory, the law of conservation of matter. These are the people who are credited with discovering the structure of the atom. These are the different particles that we have, the nuclear model of the atom. You should know this one as well. Atomic number, atomic mass, isotopes. Okay, these are all the different properties of any atom. And then you should know the periodic table. Okay, you should know the division of it in metals, metalloids, and non-metals. And then again, what all the different groups are called. You should know all of this. Okay, so this is your little bit of a key list.